Bismillahirrahmanirrahim. Greetings. In the last previous two video lectures, I discussed the definition of function and also arithmetic with functions. Now, the composition of function was supposed to be in the video with the arithmetic of functions, but because of the length of the duration of the camera, I could not fit it in. So I'm making a new video just for the composition of functions. Now, I do encourage you to watch the previous two videos and take a good note out of it. And these videos are going to be positively beneficially to basic algebra, college algebra, pre-calculus, and also freshman calculus students. So I hope that to prove to be the case. Now, I always mention that I'm in my apartment, and under this cardboard that they may look a little bit strange to the if you watch it first time, there is a whiteboard, the dry erase, but it was reflecting the light, and I don't have the fancy looking filtering the light out, so it was giving kind of lousy videos. So I came with the idea to cover the entire board and use hang-up notes that I would be writing on the board. So please bear with me until hopefully I will have better equipment to make better, kind of more professional videos. Now, let's start, shall we? About composition of function, I have written and I have watched the videos that I had before, and looks like the notes that I am putting here, they are visible and readable, and you can take a note because you have the power of pausing and also zooming. But unfortunately, I don't have somebody behind the camera. In Arabic we say, "Ana miskin." I have no family member or somebody to zoom in and out for me, and I don't have also remote, so I don't have fancy equipment set up. So I just set it up, I aligned it so that it can be kind of large enough for you to see it. And I hope that will be the case if you wish to write the notes. I also try to read them in case if you want to write notes from my words. Okay, let's start, shall we? Composition of functions. Now, combining functions in a way that output of one of them will be what? Will be the input of another one. Now, symbol for composition of function is f circle g of x, which means f of g of x. Now, the symbol says it all. Now, with the word function always goes two non-empty sets that we call them domain and range, and then the rule of correspondence, which means the rule that corresponds these two sets together. That all these three, they form a function. That's what the whole function is about. Again, I repeat myself, in the first video about function, I went very deep into that subject. Now, what is the domain of this function, the new function that has this notation? What is the domain of that? What is the range of that? And what is the rule of correspondence for this function that has this notation presentation for us? That is the subject of this video. Okay, let's go now to the next one. By the way, this notation that I put it on here for you, let me put this one more time. No, this notation, Leibniz, the German mathematician I have mentioned in the previous video, who was contemporary mathematician in the time of Newton, he was fascinating, and sometimes, as history indicates, spending days, not hours, days, to invent notation that stands for the idea. And dy over dx and this notation is possibly from him. Dy dx 100% is from him. He is the founder of fundamental theorem of calculus, that is the marriage between a definite and indefinite integral, also the differential and integral calculus. But that is if you take a calculus, you will be seeing that one. Now, here, the notation says it all. It's fantastic. The notation says it all. Now, let me say what that means. what is the domain of this? The domain of this should come from the domain of G. G is a function. And with function always goes two sets, non-empty sets, domain and range. The domain of G, this X stands for an element from that domain, which we are in the set of reals, so X represents a real number. The domain of this function comes from the domain of G. But which domain? A domain has subsets. For example, if the domain, let's talk, is about a finite number of elements in there, then let's say n elements, then 2 to the n subsets we will have. Then from this 2 to the n subset, the subset that the range of that, which means G takes X and give another element with respect to the rule of correspondence that G has, gives an element out. Is that right? The output. The input is a number X, the output is another number, but that number is represented with this G of X. That number must land in the domain of F in order F to function naturally, and in order F circle G of X to be well defined. Do you follow what I'm saying? Again, this notation says it all. But after that, I don't really need to say anything more. I can just pack up and leave. That's it. That is the subject of composition of functions. But I have quite many examples to make it more kind of clear, especially for the beginners. Okay, now let's go to the next example, if we may. Now, in order, the notation, I just read for you in case if you want to write your notes. In order the notation F circle G of X to stand for a function, we need to know what? We need to know three things about it. What is the domain of this notation? What is the domain of this? This is a function in its own right. So what if we call it, for example, H, then I have H of X, is a function of X. Now, what is the domain of that? What is the range of that? And what is what? What is the rule of correspondence between the two domain and range sets? So this is what I have written if you'd like to take a note out of it. Now, let's go to the next one. Hopefully, you can always pause and zoom it out and make it even more clear if you like to write notes. But for my words, you can also write notes. Now, what I just said, let's discuss it through a schematic diagram. As I have said in the past, a schematic diagram can kind of improve the conceptual understanding of the subject. Now here, G takes some number. This X is a number. Again, what is X? X stands for what? X represents a number. Whatever is true for X is true for every single number that X represents, which means every single number which is in the domain of X. Domain of G. Now, here, X, I give it to, the G takes X, whatever that number is, with respect to the rule of correspondence, he gives you some number. I didn't write G of X, I just write it some N1, some real number, because we are in the set of real numbers. Then F will take that number, if it lands in its domain, and then give you another number with respect to the rule of correspondence. That another number could be same number or different. Now, if and only if, now this F circle G of X will be, he takes the X and goes directly, and he gives you N2, which means you bypass the middle one, if and only if. I wrote then and only then. If and only if you can go from here to here, then from here to here, then you can go from here to here directly, which means you bypass the second one. With examples that become clear again. Again, the notation is saying all. Now here again, I write this one, the X under G gives it now G of X. What is G of X? It's a number. Why do I write G of X? Because it's the image of X. Whatever G is. For example, if G of X is X squared, if I give him 3, he gives me 9. 3 is a number, 9 is a number. 9 will be g of x, 3 will be x. So I give him x, he give me g of x. Then g of x, f will take g of x, and then what gives it whatever is in, whatever the rule of correspondence is, to give an element, to match it with an element in its range. Now, if that can happen, if you can go from here to here, then from here to here, then you can bypass the middle one and go directly from x to f circle g of x. Which means what? I have written for you, f circle g of x is well defined if and only if you can go from this to this, and you can go from this to this. From x you can go to g of x, and from g of x lands on the domain of f, f can work with that, then he gives you, then this function f circle g will be well defined. Now, otherwise will not be. I will have question, I will have examples here that this is not the case. So let me see, I have a question here to ask. Oh, that's a good question I'm asking. G of x is 2x. So the rule of correspondence for g, whatever number you give to him, he multiplies it by 2. So g of x is 2x. What is f of x? F of x is the square root of x. What is the rule of correspondence? Is that whatever you give from the domain of f should be all real should be all positive, including 0, which is non-negative real numbers. Now, when you give it, he takes a square root of that and give it. That is the rule that f will function, f will operate. Now, we want to know what is f circle g of x, which is what is f of g of x. Now, you may come to the conclusion quickly and jump, and you say f of g of x equal to 2x immediately. And then when we ask what is the domain and range of that, here you say the domain of that is all or what? All non-negative numbers. But if the domain of that is coming from g of x, and the domain of g of x is all real numbers, so how come the domain of that become all non-negative real number? Domain of f circle g. That's what I'm going to show also for the next one in the what? In the schematic diagram. Now this one, I suppose I finished. Now let's go to the answer for this one, if I may. Do I have that? Yes. Okay. Oh, by the way, I forgot to mention in the beginning that at the end of the lecture, I also have a story to tell you, a true story by implication. So please pay attention to that story, because it also has something to do with what? With the composition of function. Now the answer of the previous question, which means g of x equal to 2x, f of x equal to that, x squared, is f circle g of x equal to a square root of 2 of x. Is it true or false? So the answer is what? Is false. Why? Because I select a number, -8. G has nothing wrong with -8. You give him -8, he multiplies by 2, he gives you -16. But when you give -16 to f, it's not in the domain of f, -16. F cannot operate with -16. So he gives you impossible task in a sense. He gives you what? Empty set. In the first video about the second video, excuse me, about the function, I did go very thoroughly about the difference between empty set and 0. Please watch that one. It's going to be very informative. Very, very informative. Okay, now here f circle of g is a well-defined function. She's asking, is it well-defined? The answer is the notation says it all. So it means what? The domain comes from g, but that subset of the domain of g such that all the elements in that subset under g fall in the domain of f. Then, yes, this notation is a well-defined function. Are you with me so far? Okay, let's go now to the next one. Now, next one is about, it's the same, but it's kind of with graph. I'm showing that. Let me secure this one, and hopefully it's visible. I'm sorry I don't have somebody behind the camera to zoom it in and out for you. so that become larger for you to see. But I think with your computer, possibly, hopefully, you could do that. Now, here, the graph, this is the graph of g of x equal to 2x. We all know that. And this is the graph of f of x equal to x square root of x. He shows it all. Now, the domain of what? The domain of g is all real number. Any number you give to him will work. Is that right? You multiply by 2, it gives you outcome. But the domain of f is all non-negative real numbers. Now, when you combine them, f circle g of x, f should take only those elements of f, those images from the domain of g, such that their image on the g will fall on the domain of what? Domain of f. Now here it looks, the reason I selected this example is because it looks like the domain of g and the domain of f of intersection of the two domains. But this is not the case. And this is a particular example. Maybe there is no other example like that. In general, definitely that is not the case. So we are not talking about the intersection of the two domains. We are only talking about what? If the range, the output of G lands on the domain, on the set of domain of F. If it does, the function is F circle G will be well defined. If not, is not. That's simple. Okay, now let's go to the next and see what I may have next one for you. No, okay, I have no schematic diagram of the same example for just extra. Now this is going to be large one and hopefully visible to you, huh? Let me see. Okay, now here the domain of G is all real number, is negative real number and positive real number including 0. And the range of that is also negative real number, positive number, and 0. G of x equal to 2x. Now, what about domain of f? The domain of f is what? Is all non-negative real numbers, which means positive real number including 0. And what is the range of that is same, square root of x. Is all what? All non-negative real numbers. Now, when I combine them together, I wish I had the ability of making this one to be like animation, and I wish I knew that art, and I could move this one up, and that will land on the what? On the range of G, that I have done it here. So the domain of what? The domain of F does fall in the range of G, but not all of it. The range of G was all real numbers. No, the range of the F circle G that I'm applying, the range of that, the domain of F will be only, I can't say half, but in a sense for just a better comprehension, you can think it's half of that. Half of the range of the G is what? Is the domain of F. Now, look what happens. If I take an element from negative from the top here, what? G does function. He give an element here in his range, but that element will not be in the domain of f, so therefore it cannot work with a negative number. And as you have seen it in this one, if I select a number here, for example -5, he gives me -10. But -10 is not in the domain of what? Of f of x. Therefore, even though it is in the domain of G, it's not in the domain of f, whatever it lands, because the -10 is not there. Therefore, the composition of function cannot be constructed. Okay. Now what is the domain? Again, the notation says it all. Domain of that is coming from the set of what? From the set of the domain of G, but those elements in the set of domain of G that they land on the what? On the domain of F. Again, let me go over that, which will be what? Which will be, if I select elements to the right of 0 or 0 for g of x, which means all non-negative numbers, what happens? He always gives me positive. The y-coordinate of them will be positive. And f can function with positive, can operate with positive number. So the domain of the composition of function will be what? Will be the set of all non-negative numbers. Again, I repeat myself, this was a coincidence that the domain of G and the domain of F were intersecting. That is not in case in general. We are not concerned about intersection of the two domains. Now, let me see, I have another example. Yes, I do, in fact. To go into that, let me take this one off, if I may, and bring the next one in. Okay. Well, as long as he conveyed the message, conveyed the knowledge, who cares how I'm presenting it? Sometimes if it is not too fancy, maybe it has a better comprehension. Now, let's see what we have here now. Here, another example I have, that g of x equals to -3. And then the f of the domain of the g of x is all real numbers. Anything you give to him is a constant function. He gives you always what? -3, no matter what real number you give to it. The range of that is -3, is a single point, -3. Now, the f of x is defined to be a square root of x. The domain of that is all real number, excuse me, all non-negative real number, which means positive including 0. And the range of that is same also, non-negative real number, positive including 0, union with 0. Now, what is f circle g of x? What is f of g of x? G of x, whatever I give to him, he gives me -3. But f cannot function with -3, cannot operate with -3. I give -3 to f, he gives me nothing. He gives not nothing, he gives me empty set. It's just a stop. So here I said the composition of them is empty set, which means you cannot compose them together. These two functions cannot be composed. Okay, now let's go and see what I have for the next one. I think I have possibly the representation of that with the schematic diagram to take you more into the better subject. This is the first one I said, really for the calculus student is sufficient, but the beginner and basic algebra student, they like to get more into the depth of the subject. Okay, here the domain of G, same thing, same problem, is all real number. The range of that is a single value, -3. And the domain of F, same problem, is the square root of x. If you remember, the domain of F is what? Is all non-negative number, and the range of that is also what? Is all non-negative number. Okay, now this is the graph. This is the graph. Now, whatever I give to him, he gives me -3. But -3 is the outcome. -3 is not in the domain of what? In the domain of F. Therefore, these two functions cannot be constructed. Alright? Now, this is the schematic diagram of that the domain of G is all real numbers. The range of that is a single value, -3. And then domain of F is all non-negative number. You see, they do not intersect. The range of G does not intersect with the domain of F, therefore F circle G cannot be constructed. Are you with me so far? Okay, now let's go to next. Next one is, let's see what I'm doing, I have here. Now, again I have same thing, but I say, what about if I have G of f of x? Now, to show that composition of function is not commutative, which means f circle G of x is not same as G circle f of x in general. Alright, then when we go to the inverse of a function, we will come up to see to be the composition of them end up to be what? Identity. And I will be putting one entire lecture just for the inverse of function in the possibly next video. Okay, here, how about g circle of f? We know what g of x is what? G of x was -3, f of x was square root of 3. Now, g of f of x is g of f of x. What is the domain of f? What does domain of f was all non-negative real numbers. And g had no problem. You give him negative or positive, he always give you -3. So you had no problem what you give to him as an input, any real number. So if I'm giving non-negative real number, what does he do? To f, he give me again non-negative number, and g always give me -3 out. So g circle f is perfectly defined, is a well-defined function. F circle g was not, g circle f it is. So that proves that the composition of function is not commutative. 2 times 3 is not same as 3 times 4 in this case. Do you follow? Okay, because multiplication is commutative. Now let's see what I have about, I think I have another example. Yes, I do. This is also a good example. What is the domain of this f circle g of x if it is defined to be x plus 1? So what is the domain, again, let me repeat, what is the domain of f circle g of x if f circle g of x equal to x plus 1? Now you may think about, okay, let's say f circle g of x is another function, let's call it h of x, h. Then I will have h of x equal to x plus 1. And what is, if h of x equal to x plus 1, then what is the domain of h? So you said the domain of h is all real numbers. Is that right? But in the composition, you must be very careful. You cannot say that. You cannot say, because this is x equal, at the first glance, for the beginner, in the test you will see a lot of them, that they say the domain is all real number. So right now let's prove that this cannot be the case. Now, the answer to this question have to know the domain and range of f and g before we come to that conclusion. So let me give you a counter example to show that this may not be the case. Now, the counter example I made is that let f of x to be x squared plus 1. And then g of x to be a square root of x. Let's see now, take a good picture out of it before I go to the next, if you write any notes or something, so that I can discuss the next one. I have f of f and g for you. So now let's go to the next and see what I can give you next one. So what is f circle g of x? Which means what is f of a square root of x? Is that right? Now, f takes a square root of x and I square it, which means it gives me x. And then plus 1. You remember the rule of correspondence for f. So it gives me x plus 1. Is that right? Now, since the domain of g was the whole, in this case was the whole non-negative numbers, the domain of that, and the domain of f circle g will be what? Will be all non-negative real numbers. So their domain, even though it ends up to be x plus 1, the domain is not all real number. Why? Because the domain of the domain of g was not all real number. So the domain of that comes from where? From the domain of g. And the domain of g was all what? All non-negative number. Therefore, the domain of the composition of the two functions must be all real, should be what? Should be all non-negative real numbers. Okay, non-negative real numbers will be the domain of f circle g. Now let me see what I have next. Next is, yeah, this one I am finished. Now I would like to talk about the application of that I don't have to put anything up for you. Now, the composition of function has very, very important application in calculus, in differential calculus. They call it a chain rule. Chain rule is based on that. So once you comprehend this one very well, when you go to chain rule in your calculus, it becomes much simpler. And if it is in calculus, of course, I will be putting some tapes, videos of that. I will take it more into the detail of that subject. Now, the other application that you can think about the composition of function is about transmission of your car, the gears. The gears of the transmission of the car are constructed based on composition of functions. Now, I'm not very artistic, but when it comes to the calculus, I have drawn a very nice, beautiful picture. That was artistic enough to give you beautiful that how the gears are working based on composition of functions. And now, the old time, I'm old enough to say that in my time, we didn't have electronic clock and watches. This electronic watch and time really revolutionized the world. It was fascinating technology. Before we had all the watches were mechanical, and Switzerland was the master for them, and all of the companies, they closed after the technology of the electronic watches came out. Now, the way that they were constructed, the way that they were functioning in the clock or in the grandfather, whatever they call it, clock, all of them were based on composition of functions. The gear, the mechanical gear of them was based on that. Now, the mechanical rotation, you can say, of each circular disc in the watch. But that is most of the students nowadays they are dealing with what, with the electronic watches, so they don't know what I'm talking about. Now let's not talk about the story that I told you. I will tell you. Now this is a true story. Now a kangaroo and a rabbit, they come to argument. The kangaroo kind of sarcastically says to the rabbit, "Hey shorty, I can run 10 times faster than you." Now the rabbit says to the kangaroo, "Hey, not that fast, man. Just prove it. Let me go to the referee or to the judge, let's race together." Now the rabbit says that I can go, if I can run 10 meter per second, then in order you prove that you said right, you have to go 100 meter per second. Now kangaroo doesn't know what meter per second means. He's in Australia, but the rabbit does. So they go and they race. Now the kangaroo is always looking back to see if the rabbit, how far back he is. Is he 10 times ahead of him or not? So the kangaroo is a function of rabbit. And the rabbit is a function of time. So the rate of change of rabbit, if you go in 5 meters per second, is a function of time. The rate of change of kangaroo is what? Should be 10 times that, which means 50. Which means what? Which means when you go to chain rule, you will get that the chain rule notation of that. I don't want to go through that. F circle g of x is g prime of x times f prime of g of x. And some of you may not know what I'm talking about until you take the calculus. So this story happened in the planet Gobbledygook somewhere, that the kangaroo and rabbit can talk, but is a really true story by implication. And I hope this story puts some kind of a smile on your face, because I always like to finish my lectures with my students living with a smile on their face. So I don't know what else I can say, except that the next video I intend to put about inverse function, and I encourage you to watch all of them. They may prove to be very beneficial to you all. Okay then, until next time, have a prosperous day, a prosperous night, and prosperous time. Oh, by the way, I shouldn't say until next time. I should say that at all the time. I wish you prosperous time. So long. Bye-bye.